Hi, I'm Matt Moores from the University of Wollongong in Australia, and I'd just like to take you through a quick demo of how to use my R package, serrsBayes. In this example, I'm going to be using another R package, hyperspec, to read the SPC file off the disk into R and then plot that spectrum. So here we have a Raman spectrum of ethanol, and we can see 6 characteristic peaks of this molecule, and also maybe a shoulder over here at about 1450 wave numbers. So now we're going to window this spectrum just to give us a region of interest, because there's not really anything going on in this region less than 300 wave numbers, or up here above 1800. So we crop that out, and it's just going to make the algorithm slightly more efficient and save us a bit of CPU cycles. Now, because this is a Bayesian method, we need to define informative priors for all of the parameters of our statistical model, and that includes the peak locations. So you could get these peak locations from doing DFT analysis of the molecule. In this case, with ethanol, I've just looked up these peak locations from a paper in the literature. And so this then defines our priors here. And here we can see, circled in red, these are the peaks according to our prior. And you can see that they're not exactly correct. They're a little bit off, but that isn't going to matter as far as the R package is concerned. Now, I'm going to skip over this step for the interests of time. On this Windows laptop where I'm running everything, it takes around 10 minutes to run the algorithm. So this is one that I've prepared earlier. The other thing I'll note is when you do run the algorithm, it prints out a whole bunch of diagnostic information, basically to let you know that it's still working for the 10 minutes. And then if everything works, this kappa will be equal to 1. So we can see at the previous step, it was like 0.965 or something like that. So once we get to kappa equals 1, the algorithm stops, and it's taken 36 iterations of the algorithm. And that's taken us 10 minutes of elapsed computation time. I think I've got 4 CPU cores on this laptop, and so it will run in Windows. It'll run the computation in parallel. You can also install this R package on Mac or on Linux, and probably the better way to run it, if you can, is on a Linux server rather than running it on your own laptop, because it can, your laptop can get a bit warm when you're using all of the CPUs. So that's our elapsed time. So the next thing we're going to do, so we have 3,000 particles, which represent 3,000 samples from our posterior probability distribution. But for plotting the results, we don't really need to be plotting 3,000 points. So I'm just going to take a subsample of 200 of those points. So in black here, we have our original Raman spectrum. And then over the top of that, I'm going to plot 200 samples, independent samples, from the posterior distribution. So green is a fitted model, and we can see that we've got very good fit between the model and the data. I'll just expand this a little bit. There's just a couple of spots here where we thought there might be a shoulder, and over here as well. So if we're being really fussy, we might add a 7th or even an 8th peak to the model. But these shoulders are not really quantitative, and so it's not going to make a huge amount of difference for our analysis. The next thing I wanted to show is the other things that we can get from this posterior distribution. And the first one is an estimate of the location of each peak. So before I said it doesn't matter too much how accurate you are with your prior. So this red line is the original prior that I had for the location of this peak number 6. And this blue curve here are 2000 samples from our posterior distribution. So we can see that our estimate after we've analyzed the data is very different from what we originally thought based on the literature. And we can do this for every peak and see that we've got an updated estimate of all of these peak locations based on the data. So this blue one is based on both our data and our prior, whereas this red one is just our prior distribution without looking at the data. We can also get posterior distributions for other parameters of interest, for example, the amplitude of the peak, and we can then compute things like 95% intervals for the limit of detection and the full width at half maximum of each one of these peaks.